right. All right, thank you, everyone. Thank you, everyone, for coming. So I'm Stefan. Yes, take your laptop, maybe. You good? Thank you. All right, so I'm Stefan. I work at Wolt. Tonight, I'm talking with two other people. They will introduce themselves later. And tonight, I'm going to be here to talk about how Wolt is using machine learning for logistics topic. And on my side, I work on the machine learning platform. So I'll focus on the machine learning platform. They'll talk about logistics. That's the plan for tonight. So yeah, quick content, quick intro about Wolt. Maybe you don't know us. So it's going to be sales speech for 2 minutes. Then it's what you're interested in. So Wolt started in 2014 in Finland. We're now in 25 countries, 500 plus cities, 29 million clients, I think now. A lot of people, a lot of restaurants, a lot of core partners. So there's a stats. You're not really here for that. We go from Iceland to Japan. So that's it. I have one more? Yes. Sorry, the clicker is laggy. There you go. We have different product teams because we have one app technically for you, but we also have apps for merchants. We have app for couriers. We have B2B. We have Wolt Market, which are supermarkets. We have a lot of different product teams. And usually if you work as an engineer, you're going to be in one of those product teams. Then we have 5 tech hubs, Helsinki, Stockholm, Berlin, Tel Aviv, and Tokyo. And that was it for the sales pitch. I'm done. Now we can do a tour of the machine learning platform. All right, so ML at Wolt. We have different use cases, and we have like supply and demand forecasting, which is, okay, next week, how many people are going to order? How many courier partners do we need in the street? So that's what we forecast. We have recommender systems. Let's say you move to a new city. We're going to be like, okay, like which restaurant you may like. You order a lot on IKEA, for example. Maybe which thing you may want to order next. Logistic. I won't spoil the content, so they will talk about it. We have fraud detection, and we have support prioritization, and then we have new use cases coming later during the year, but I can't talk about them. So we have different use cases, which mean different needs. Our data scientists, they obviously need access to data. You want them to access production data, but you don't want them to access everything in production. So it's also like, how do you do it to make it simple and yet safe to have access to production data? Also infra access, like now everyone needs GPUs for like the past months because everyone is like doing LLMs. So those things, so like, how do you get access to GPUs? How do you make it easy for them to access to GPUs? How do you make sure they have enough CPUs when they train their models, enough memory? But you want that to be easy. So that's another thing. You want them to deploy quickly. You don't want them to struggle to deploy something. It has to be easy so they can have like more impact. They don't have to struggle to be like, okay, how should I deploy that? Oh, I don't really want to deploy. It's really nice in my notebook over there. I want it to stay there and never go to production. So you don't want that. So like, how can you make that to be fast and easy? And then monitoring, which is the last part. You want to track everything. You want to make sure that your model is good. You want to make sure that also the performances are good. Let's say the latency and different monitoring. And you don't want the data scientists to write the same code every time, because first, most of them don't really care. So you have to do it automatically because it's not part of their job. So then like, how do you do that automatically? How do you make sure that it works for every model? So those were the needs we had. And quick intro as well for people that don't know about ML lifecycle. It's always the same. So you have like the research and development part. So you have, you formulate a problem, you get some data, you do some ML a bit, you play around, then you have your models, and then you evaluate them. You make sure that you're happy or not. And then once you're happy with one, you go to production. You deploy your model, you monitor it, you evaluate it, and you go back to research and development and you iterate. And that's really like the entire thing we want, is to iterate quickly and make sure that ML, we can solve all the challenges we had before, because we had a lot. So yeah, like there was one challenge, which is like, we only had a couple of projects that existed. And for the new project, it was also very hard to launch them because you were like, yeah, I don't want to deploy the project, or I don't know how to access GPUs, all those things. We had a lot of different tools. We had Airflow, cron jobs, SageMakers, custom code running on our clusters. It was not pretty. And then the impact was also not always known because you couldn't monitor everything. So it was like, okay, like I have my model. Is it working? I don't know. It's working well. I have no idea, but we have a model running. So it was hard to measure everything. So those were the challenges. And we're like, okay, let's focus on one thing, make iteration very quick and very easy. My screen's black. It's back. All right. So yeah, so what did we want for the ML platform? First thing, product thinking. As I said, launch new project easily, iterate easily. Driving force for new projects. You don't want the ML platform to be a blocker for new projects, and make sure that data scientists can do things quickly and they have like a lot of velocity. Yeah. All right, a lot of toolings as well. You avoid having them to write boilerplate code. There's always the same. Have common best practices as well, like how do you write tests? What should you test? Have templates as well they can use so they don't have to like define the same code all over again. And a lot of automation, a lot of CI/CD, so they don't have to do it, and then they can just deploy automatically without having to think about how to do CI/CD actually, how to write GitHub actions and those things. And the impact, have monitoring everywhere by default, log everything by default. And then I think we'll talk about that later. And at first, we had Airflow. It was like 2.5 years ago now. And it was good, it was nice, we're happy. But at one point, we're not happy because they don't support dynamic tasks. They didn't really in 2022. So it means that you couldn't generate tasks at runtime. So you couldn't be like, oh, how many tasks should I have? I don't know, let me check my database. How many cities do we have in the world? And then you create tasks for all the cities you have. So you couldn't do that before. Now you can. You have to explicitly define the task dependencies, which can be annoying. Like you have task A that has to run, before task B, you have to define it explicitly, which is not the best. And then you have no caching. So it means that you transform your data, and let's say you're going to train a new model with the exact same data. You have to rerun everything again, which is not optimal. And then it's also not really designed for ML. So that was a bit of a pain. And then we went with something else, which is open source, which is called Flight. It was developed by Lyft in the US, and it's fully open source. And what's good is that it's Kubernetes native, so our whole infrastructure is running on Kubernetes. And then it supports automatic prioritization. So let's say you have 2 tasks running. You have task A, it doesn't need anything from task B running. You don't need anything from task A. It's going to run everything in parallel. You don't have to define everything. Like it does it for you. It has version, reproducible pipelines as well. It has caching. That's probably one of the best things. So if you train a new model on the same data, you don't need to like transform it again. Or if something crashes and you take 6 hours to train your model and it crashes after 4 hours, then the first 4 hours will be cached. So you don't have to do it again and you're not losing that time again. And it has different SDKs and it has dynamic workflows, which is also really nice. We use it to train our model per city or per country. We have like more than 500 cities now. And imagine, you don't want to change your code every time we add a new city because we add cities every week, basically. So you just go like over the list of the cities. And then if you have 500, then it's going to create 500 workflows for you. And you don't have to think about that. So yeah, that's why we use Flight. We've been using it for a year now. I think people are happy, but I don't know. And then the whole ML platform, so the entire ML platform is open source. And that's what we have. So I have Flight, ML flow to experiment tracking, a fancy database with a UI, basically. Then we'll have Python. And the last one is Seldon Core, which is what we use to deploy our models to production. And it creates nice microservices, automatic logging. You have A/B testing, can do canary deployment. Yeah, it is nice. So yeah, that's the whole ML platform we have. And that's what our data scientists are using. And now the mic is yours.
Thank you. Can I take the clicker?
Yes.
And yeah, perfect. So now hi, I'm Kassu. I work as a data scientist in the logistics team. And so I'm going to talk about how do we utilize these tools that were just represented here. Okay, cool. same sales slides that Stefan showed. I'm gonna speak about a little bit in terms of like, what does this mean in the eyes of a data scientist? So if you look at that, you can see that the scale is pretty big. So you can imagine that this like data, the context is pretty heterogeneous. And this creates you a lot of potential for ML and data science solutions. So one task that us in logistics are responsible for is providing customers with delivery time estimates before they place an order. And just in terms of like looking at this, you can pretty much imagine that it's pretty different, operating in Iceland versus operating in Japan. So just think about like what the cities are like. Some cities are more densely populated, some cities are more sparsely populated, some areas are big and deliveries take a long time because of longer distances. Some cities have better infrastructure for using certain vehicle types. And yeah, so this is just in terms of like how is it to actually deliver stuff. But then if you consider the merchant side, we have a lot of merchants, like over 100,000, and these can also be of broad variety. They can be either restaurants, they can be retail stores, they can be pharmacies, they can be franchise businesses, small local businesses. They can so even with this categorization, they can have very different kind of traffic in terms of purchase volume. So this really creates you a lot of opportunities in terms of what you can do with this kind of context in the data. Also brings a lot of challenges because of the availability and quality of data, because you can't just assume that you have lots of data from certain venue that, oh, let me just compute aggregates. But what if the venue has very little data? They have a single purchase per day. What kind of aggregates are you going to compute then? But so yeah, let's come back to the point where we have this use case of providing customers with delivery time estimates. So it probably comes as no surprise that we have a machine learning model that estimates these delivery times. But let's, for the sake of a good story, let's just assume that we're only now gonna build that product, or that feature to our product. So someone comes up and, hey, we scoped out this problem. We want to roll out this model that estimates the delivery time. And well, you enter your development cycle, you plan, you reiterate, and yeah, repeat this until you're satisfied with the model performance, or you run out of time and are forced to hand in the model. But yeah, so you managed to develop a machine learning model locally. But then what still misses is that how do we then serve these estimates to our customers that are browsing the app and want to see how long would it take if I went to order from here. So how do we serve these estimates to our clients?
Hi, I'm Anil from the logistics team, and I'm a software engineer. And this is where basically our data scientists hand over their models to us. See how the clicker does. Yeah. So yeah, how do we? So let's imagine that we have a model that lives as an artifact in some remote storage. So how do we deploy this in Kubernetes, and how do we ensure that this is callable and returns predictions for delivery estimates? Well, deploying it to Kubernetes comes with many different challenges and many different considerations, and this can be overwhelming to manage and to unify across many different apps. So we basically make use of a unified solution to make this more manageable. We use an open source tool called Seldon Core, which Stephen already introduced, which our ML platform provides for us. Seldon Core takes care of most of the boilerplate in productionizing a machine learning service. A simple Python component for Seldon Core can easily look like this. Let's see if we have a clicker pointer thingy. Seems later not really working. But we can imagine that we can have, with a simple code snippet, we can load our model, define our custom inference logic, and at the very end of it, call the predict method of our model. And then Seldon will take care of wrapping this as a Flask and unicorn-based microservice with a gRPC and REST interface. Seldon is Kubernetes native and takes care of quite a lot of the heavy lifting in terms of managing Kubernetes resources. It provides a custom resource definition to help configure your deployment. What's also nice about Seldon is that it's agnostic to the machine learning framework that you're using. It provides language wrappers for a big variety of languages and also supports monitoring and observability through request and response logging, tracing, and metrics. For example, it provides custom Prometheus metrics, which, for example, for CPU or memory utilization, throughput, latency, or errors, which enables you to build Grafana dashboards to monitor your services. I mean, this dashboard is from some test data, so don't think that the graphs will make any sense.
Cool. Then to touch the flight part of it, so we produced a model, machine learning model offline, and we were able to set up a microservice. Then what we probably would also want to have is like consistent performance over time. So how can we achieve that? We know that, you know, concept drift happens, and if you don't account for it, then the performance will degrade over time. So to account for it, we can just, you know, or one way to account for it is to retrain your model periodically. And we do this by using Flight. What's really convenient in my eyes is that what happens is that each training leaves you a trace of, you know, the bars reflect the status, so you can see successes, and in case failures start occurring, you can also see failures. And even better is that you can also, like through Flight's UI, you get the visibility to logs, so you can more easily track the failures for like, why did my model training workflow all of a sudden start failing? So it might be happen, for example, you increased your memory size, but you forgot to increase your resources defined for the workflow, for example. Oh, whatever. Yeah, so that was for production use, for, you know, maintaining the model performance as is in the production system. But it's also quite handy in terms of, you know, enabling heavier research use. You know, local notebooks are okay for doing POCs and, you know, coming up with something, but then as soon as you want to actually start getting more systematic and finding out like, hey, I need to do like heavier hyperparameter tuning, or you want to explore with different like data selection strategies, or, you know, just try different models, then obviously, you know, as you increase this, you know, search space, then, you know, you all of a sudden find yourself training models for, you know, days, which on your local laptop is not maybe the optimal thing to do. So you can do this like heavier model trainings also through Flight's UI, which is pretty nice. You can, you know, just put some, I don't know if it's visible, but a prompt opens and you can specify inputs. You can obviously configure these, like what kind of things you want to input, but lets you trigger things manually. And as Stefan mentioned, it supports caching. So you can pretty easily see, for example, like if you fetch data, that fetching it once is okay, but fetching it every time is maybe not that nice. So the caching functionality really plays a nice role here. And also one thing I'm going to mention here is that executing workflows is actually bound to like commits, which, you know, with a fellow data scientist really facilitates the sort of co-development of a project and a workflow even. So that's, I think, a really nice use case. But in any case, let's say that, you know, we go through all this, continue development on the delivery estimate model, and we come up with some improvement that we'd like to then take to production. So we have the existing production model, and then we have this new candidate that we'd like to roll out. Then how do we go about?
Yeah, so thanks to Flight, now we have a systematic way of iterating, and we, based on these iterations, came up with a nice candidate model to replace, or potentially replace our new model. And so how do we evaluate whether this new model is actually fit to run in production? Well, first, we want to expose this model to production traffic. But then how do we do that without actually impacting the production service that is actually live at the moment? Well, we can use shadow deployments. So Seldon enables to define a second predictor and to basically flag it as a shadow deployment. What this will do is that all the requests that reach our main model will also be reaching our shadow model, but all the responses will be discarded. However, Seldon still enables to log them. So with this setup, we basically have the possibility to monitor our model both basically on the model side and also on the technical performance side. From the model performance, based on the logs of the responses, we can see if the predictions that we get are as we expected. And from the technical performance side, we can observe whether the new model actually introduces any bottlenecks, for example, in terms of latency, or for example, in terms of memory or CPU utilization. So let's say we ran our shadow model for a while, we gathered enough data, and we have an idea whether our model is passing our evaluation. So we managed to get, let's say, a model that passes our evaluation. What is next? Well, we want to know whether now this model actually makes sense in terms of the business, in terms of our business metrics. So, and how do we measure this? Well, at Wolt, we have quite a strong experimentation culture, and we also have our own experimentation platform, which enables us to test features before fully rolling them out to our customers. I'm pretty sure most of you have already heard about A/B testing, but essentially what we mean by this is basically to introduce one version of a feature to one group of users, for example, as a control group, and introduce a different version of the same feature to a different set of users. This enables us to basically observe our candidate model in a controlled way in the production environment. So for the A/B experiments, we use another feature that is provided by Seldon, which is a header-based routing. This is also enabled by the underlying API gateway that we use together with Seldon. So in comparison to the shadow model, instead of deploying a second predictor in the same deployment, this time we deploy a separate deployment, which we could, for example, call as a canary deployment. But we add two important things. So basically we add two annotations. One is a reference to the main model that we already have in production. And the second one is an arbitrary header. What this enables is that basically both our main model and our candidate model can be called from the same endpoint. However, the requests that have the header that we defined in these annotations will be directed to our candidate model. So with this facility, then we can distribute our traffic using our experimentation platform. For example, with 75% of traffic going to current model and 25% to our candidate model. So once we run our experiment and gather enough, let's say, sample data, we then have an idea whether basically our new model makes sense in terms of business metrics. And well, in case it does, then it means it's time to celebrate because we have a new model that's ready to be in production. And well, in case it doesn't, well, you know the story. We go back to the beginning of our machine learning cycle. Yeah, thank you so much for your attention. We hope that this was an interesting presentation for you, and that we hope that we also were able to spark a bit of interest in Wolt for you.
Yes, he did it.
So we have a quite variety of positions that we're hiring for at the moment. So if you're interested, please feel free to check our career website. And yeah, thank you again so much for your attention, and we'll be glad to take your questions.